All right, happy Monday, everybody. Welcome back. Nobody is a frozen block of ice yet. No, it's close. These are like the days I like wearing a mask outside. It's the one advantage, right? Okay, well, welcome to Fluids today. We're gonna pick up and cover, I don't know how much we'll get, but most of fluid statics today. We'll probably have some to pick up on Wednesday. Just a couple notes about things that are happening over the next couple weeks. So this week, there's a homework that's due Friday. It's relatively short. There's going to be another homework that I'm going to assign Wednesday. So they'll like kind of overlap just because I made the last one due Friday. I probably should have made it due Wednesday, but such is life. So I'm going to assign it Wednesday so you have enough time to work on it. It's not going to be super long. That you'll have a week to do. So you'll have like from Wednesday till next Wednesday. So I'm going to throw that. Holding things is hard. So they'll kind of overlap a little bit. I think especially this next assignment's going to be a little bit longer than like this week's assignment. So just know that, but I think it shouldn't be a crazy amount of work. That's kind of in preparation for a week from Friday, right? We're already coming up on our first exam. So first exam, a week from Friday. We're gonna have a quiz a week from today. So I'll go over this again on Wednesday, but we're gonna have a quiz a week from today, which will cover some of the stuff that's on like the next homework assignment and the final exam. So the exam is going to cover stuff, and again, we'll go through all this just so you have some idea. The exam is going to cover stuff basically up through homework 3. So homework 1, homework 2, homework 3. That's kind of the section of the class, which is through today and tomorrow and maybe a little bit of Friday. We'll see. So that's going to be kind of where things are headed. So look out for some of that stuff. Again, I don't think you really need to worry about it right now, but just kind of where we're headed over the next 2 weeks. So just keep your eyes out for some of that stuff. And I'll have that on Moodle and we'll keep you updated throughout. What we talked about last week, Friday, we introduced and kind of went through the basic equations of fluid statics. Right, so we talked about fluid statics, right, which is just where we have fluids that don't have any acceleration. So whether they're in constant motion or if they're truly static, we just mean a fluid that's not accelerating. The general equation, which we derived, was that the gradient of the pressure equals density times the gravity vector. Right, I think we wrote it a little bit differently, but this is the general equation. We have a simplified equation if G is only in the Z direction. So if it just so happens that gravity is pointing down and it makes the most sense for us to put our axes pointing down in the same direction. It doesn't always, and we'll see examples where that doesn't line up. Then we only have to care about the Z direction, so we would get dP dZ equals rho G. Or we could split our differential and integrate. So we'd have delta P and delta Z. Right, so we could write this, or delta P equals rho G H. We can do that if density and gravity are not functions of pressure and height, respectively. So if density is not a function of pressure, this works. If gravity is not a function of height, this works. These are mostly always the case. Not always the case, but mostly always. This H is the fluid depth or height. There. Okay, so this is kind of where we ended. We can use this. We have and I'll leave it as delta P for a couple reasons. We'll see it as we go through some example problems. But the way that you can think about this is, say, you're looking at a fluid out here. So this is, say, the ocean. Right, and there's the bottom of the ocean, and you want to say, what's the pressure at the bottom of the ocean? That's going to be your height, H. But up here is the atmosphere. So there's a pressure, P, we'll call it P naught equals P atmosphere. So above the surface of the ocean, it's still some pressure, it's atmospheric pressure. We could write the equation for P, we'll call this P floor. We could write an equation for P floor with this. So P floor minus P zero, that's our delta P, is equal to rho G H. So you're always talking, when you're talking about pressure changes in fluids, the P is a delta P, and it's, right, you can think about it like, how much does the pressure change as we're going down through the fluid? It changes by rho GH, which is simply just the weight of the fluid. So another way of thinking about pressure and fluid, what is the pressure? Well, it's the weight that's sitting on top of your head. And I think that's the easiest way for me to like remember it. And especially when we get into more complex geometries and stuff, it's the weight that's sitting down on top of you. That's what's giving rise to the pressure. So it's just rho GH. This example brings up kind of an interesting point, because there are two different ways that we typically talk about pressure. We'll call it the pressure reference. If we think about how we measure and talk about pressure, we do it in two ways. If I asked you, say your bike tire is flat, and I ask you, what's the pressure of your bike tire? Say 0 PSI, right? But that's not actually true, because there is air inside of your bike tire. It's at atmospheric pressure. It's not actually 0 PSI, which would be a perfect vacuum in absolute pressure. So we have kind of two ways of talking about it. We would say, like, what's the pressure? It's 0. But 0 what? Like, is it a perfect vacuum, like there's nothing inside, or is it atmospheric pressure? So those are kind of the two systems we work in. One that we call absolute pressure, and one we call gauge pressure. So I'll draw a picture that hopefully will help explain. So if we have pressure here, there is a 0 pressure, kind of like there's 0 temperature. So you can think of this a little bit like Celsius versus Kelvin. It has some differences, but 0 pressure is there's nothing there, right? There is no gas, there is no nothing. It's a perfect vacuum, that's space. So P equals 0 is a perfect vacuum. Okay, so there is a floor to what pressure can be, and it cannot go below that, just like there's an absolute 0 temperature that you can't go below. What we typically measure, though, is based off of atmospheric pressure. So typically, if we're measuring, say, a pressure here, we measure that. There are two different ways that we can do it. So say that's a pressure above atmospheric pressure. Atmospheric pressure is somewhere there in the middle. So atmospheric pressure, we could measure this pressure here, right? This is our measured pressure up there. We could measure the difference between a perfect vacuum and the pressure that we're measuring. We would call this P you can't read that. It's P absolute, the absolute pressure. That is measuring from 0 to what we're measuring. But typically we measure this pressure. So when you're measuring the pressure on your bike tire and you say it's 0, it's because it's 0 on this scale. Or if you measure your bike tire and you say it's 40 psi, I'm ready to go, it means that this difference, the difference between atmospheric pressure and your bike tire, is 40 psi. It's not the difference from a perfect vacuum, not like the whole scale, it's just that top part. We call this P, typically it's P gauge. And why do we call it P gauge? Because you use a pressure gauge to measure it. So this is the pressure that, like a normal pressure gauge, like a pressure gauge on your bike pump, that you're measuring the pressure on your car. If you have like some industrial piping system and there's a pressure gauge on it, this is like the pressure that it's measuring. So the gauges that we typically use for measurement are measuring this difference, which is just, right, so this would be the difference between 0, this is P atmosphere. So most pressure gauge, this isn't true, but most pressure gauges measure relative to the surrounding atmosphere. So for example, if you take your mountain bike and you pump it up to 40 psi here, or you let out the air and you take it to Colorado and then you pump it up to 40 psi, the absolute pressure in those two cases is going to be different. The gauge pressure is going to be 40 in both cases, and it's going to feel just the same, but the absolute pressure is going to be different because atmospheric pressure will have changed. So it's relative to the surrounding atmosphere. It's not relative to, like, you know, nominal 1 atmosphere. It's relative to whatever happens to be around it, relative to the surrounding atmosphere. So often we'll talk about, and you'll sometimes see gauges like this, where you can measure like what the vacuum is in like a negative pressure. So sometimes you'll see a negative pressure. Negative pressure doesn't mean anything. Like, how can you be in negative pressure? Well, you can be in negative gauge pressure. So that means like how far below atmospheric pressure are you? Or you can be a positive gauge pressure, how much above. But these two different pressure systems, it's easy to mix up. I think of it just like we think of Celsius and Kelvin. But it's not quite that straightforward because there isn't a consistent like translation between the two. You can't say, you know, I add 1 atmosphere to the gauge pressure and that gets like nominal 1 atmosphere, 101.3 kilopascals, whatever it is. You can't just add that every time and get there. You have to add the surrounding, whatever happens to be the surrounding pressure that you're at. Does that make sense? Okay. I think it'll still be, we'll probably mix it up some, but I think this picture hopefully helps. It's easy to mix up. Most of the time we're measuring gauge pressure, but just a note, we need P for PV, right? So if we're doing some calculation, oftentimes we need the absolute pressure. This is one example. If we're doing things, we talked about this a little bit, but if we're doing things for measuring forces or whatnot, we often don't need the absolute pressure. You just need the relative pressure. Because right, pressure difference is what matters, not the absolute pressure. Just like you don't feel the fact that you have 1 atmosphere of pressure on your head because you also have the exact same pressure inside your body. So everything is balanced out. So when things are like that, often we just need the gauge pressure, which is like how far above we are from the surroundings. Okay. So one class of problems that is pressure measurement. So we're going to spend a little bit of time these work fairly well just to kind of as instructive systems for this. They're also relatively common systems because this manometer is like the easiest, cheapest possible pressure measurement device. So they're widely used because you can't find an easier, cheaper, more reliable pressure measurement device. Like you can't, it's hard to, so they're used quite frequently. For example, if you've used or if you remember using in Engineering 101, if you remember using the wind tunnel, I didn't take a picture of it, I should have. Maybe I will and send it out later. But we used to measure wind speed. You measured that with a manometer. You maybe don't remember that, but we'll do some of the math for how that actually works in this class later. Right now, we're just doing like how would you read a manometer. So a manometer is something where this is a cross section. So this would be, let me draw a better one. This is like a pipe going in and out of the page. Then there would be a tube to some second pipe here, and we'll call this, what we're interested in is the pressure in these two tubes, or the pressure difference in these two tubes. So we would call this P1, this P2, and say there's fluids in these two tubes. If we had, just kind of keeping this general, and we'll do an example here soon. There's a fluid in the manometer. For example, if this were measuring the pressure, say in those two pipes say that's water, we could use an oil manometer. So two fluids that don't mix. Or if it's air, we could use like an oil that's not going to evaporate or just going to sit there. So we have two different fluids that aren't going to mix somehow, whether it's a liquid and a gas or two different liquids that don't mix. Or it's like a liquid and mercury or something like that. So there are lots of different ways to do it. What's going to happen is the pressure, like P1, is pushing down on one side of the manometer. P2 is pushing down, as I've drawn it, a little bit less on the other side. So we've kind of like, right, so I think of these, and we're going to do the math for it, but I think of it as like two hands on one of those old timey scales. So which one gets pushed down, then the other one gets pushed up. So on my left, your right, that hand has more weight on it at P1 than we do at P2 because it's kind of tipped the scales in that direction. So how we're going to solve these is, so think how I think of it. Of a scale. So P1, this is, again, not P1 weighs like P1 weighs more than P2. The way that we're going to be able to calculate pressure differences for these things, we know pressure increases down our fluid column, right? We have delta P equals rho G H. So pressure is going to increase, the weight is going to increase as we go down our fluid column. And then this is kind of the key thing that we're going to use. So any 2 points at the same elevation in the same fluid are at equal pressure. Okay, so what that means, if we go up to my picture, if we look at the pressure here, we'll call that PA. The pressure at the top of the dark fluid, whatever that one is, that has to be the same as the pressure here, PA prime, the same elevation in the same continuous stretch of fluid. So this PA is equal to PA prime, right? The way to think about that, from PA, so pressure goes up as we go down. So we go down, pressure goes higher, 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 higher. So, and then as we come up the other side, pressure is getting lower, 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 lower. So we go down some amount, say 10 centimeters. We go up the same amount. We're back at the same pressure. That makes sense? Okay. So I'm not going to prove it more than that, but then what we can do is say, okay, so if the pressure at those points, PA and PA prime, if those are equal, then we can kind of do, what I do is think of, okay, so those are two arms of scales that have the same weight sitting on top of them. Weight, same pressure. So we can say, okay, what is sitting on the left side above PA? What is sitting on the right side above PA prime? And those two things have to be equal. So we could say, okay, PA, so pressure at say P2, if we wanted to figure that out. How would we do that? So we know, okay, so PA equals PA prime. Okay, so PA, if we say, okay, what is PA? PA equals P1, and then you have that height, right? So there's P1, and then there's some other amount of fluid. Let's call this, this fluid rho, let's try not to confuse it. We'll call this rho alpha, and this one is density beta. So they're two different fluids, say one's water and one's an oil, or one's water and one's mercury or something like that. Okay, so this height here is we'll call this H1. That's the same height as this one. So this is also H1. This is, we'll just call that little height just H. Okay, so things are going to get a little bit confusing with some of our different notations, but okay, so what is the total weight on the left-hand side on top of PA? Everything's sitting on top of PA. Well, there's pressure 1 plus the weight of the fluid between this point here and PA. Right, so pressure 1 plus that total weight of fluid. So PA equals P1 plus, what's the weight of the fluid? Rho G H1. So this is the, I'm going to use weight on side A. P A prime. Okay, PA prime is going to be a little bit harder to calculate, but it's going to be the pressure 2 plus that first little bit, which is the fluid, or the alpha fluid, the white fluid, plus the second little bit, which is the dashed fluid. So it's like 3 different chunks. Pressure 1 plus the 2 different types of fluid. So this should be rho alpha. So this is pressure 2 plus rho alpha G. And then how much of that did we have? We had H1 minus H. So this should be H1 minus H plus rho beta G H. Okay, so this is, we're adding up the total weight on on side A prime. Okay, and the scales have to be balanced, so these two things have to be equal. So we can write that P1 plus rho alpha G H1 equals P2 plus rho alpha G 1 minus H plus rho beta G H. We can simplify this a little bit because the H1s will actually cancel out. So I'll just expand this and then we'll cancel those out, plus rho alpha rho alpha G H1 minus rho alpha G H plus rho beta G H. Okay, so if we expand it like that, you can see that term, a different color. This term ends up on both sides. So it's the same on both sides, so we can forget about it. So we have that P1 equals P2 plus, this is now rho beta minus rho alpha G H. Okay, this is the difference in the specific weight of the two fluids. Okay. Specific weight is, just rho times gravity. So the take-home message, how I think about these, and we'll do some more different types of examples. But I think of these as these two different scales and say, okay, let's add up the total weight on top of one side, the total weight on top of the other side. It have to be balanced at the same point, like a common point, like PA and PA prime. A point at the same elevation in the same fluid. That has to be a point of balance. And then we add up everything stacked up on one side, everything stacked up on the other side. If we're going down in the fluid, pressure is going up. If we're going up in the fluid, pressure is going down. So we can let's do a quick example. Yeah. Those two terms combined.
Right.
It didn't. So this is a positive rho beta. This is a negative rho alpha. Okay, I don't think it did. I think that's right. So we often will run into occasions where like the density of the two things are really different. If we have a gas and a liquid, the density of air is really small compared to the density of, say, water. So sometimes we'll run into cases where we'll just cross off the rho alpha, but just for completeness, I'll keep it in here. Let's do a quick example with a little bit different geometry. So let's say we had a manometer like this. And we have a fluid in there like that. This is mercury, Hg. This is P atmosphere, so it's open in one side to just atmospheric pressure. And on this side, we have P equals 250 kPa, and this is compressed air. So this is, from now on, you should always ask, okay, so if I write P equals 250 kPa, you should say, is that gauge pressure or absolute pressure? So I'll be explicit. This is 200 kPa gauge. Okay, the mercury has a specific gravity of 13.5. And say, for example, we, in this case, wanted to determine what H is. So okay, so that's what our goal is, find the fluid height H. Our first step is to find points PA and PA prime that have equal pressure. So that's going to be a point at the same elevation in the same fluid. So the easiest spot, it's going to be here, we'll call PA, and equivalent point on the other side, we'll call PA prime. Right, so that same height, same fluid, where PA equals PA prime. Okay, so again, at that spot, we have the same pressure up as the same pressure above each, and likewise the same pressure below each. So the pressure at PA equals PA prime, saying the same thing. I guess this should be just A and A prime, but whatever, basically the same thing. But I said find points. Okay, so PA, if we say that, right, if we go back up to our equation here, we only have to care about the alpha fluid, the air in this case. We only have to care about that if the density matters. So only if the density is close, if the two densities are close-ish, do we have to care about the fact that there are two fluids. So we'll forget about the density of air because the density of air is small relative to the density of mercury. So we'll neglect rho the density of air because it's so much smaller than the density of mercury. Then at point A, PA equals, well, there's going to be some change as we go up in the air, right? We're going, so the pressure here at that point is 250 kPa. As we go up, the pressure is going to go down. And as we come down again, the pressure is going to go back up, but that's going to be such a tiny change, again, for this reason. It's going to be such a tiny change that we don't really need to care about it. So PA, we'll say, is approximately equal to 250 kPa. Okay, it's going to be actually a little bit less than that. So a tiny bit less. But it would be a little bit less. Now at A prime, this is 250 kPa gauge. At A prime, we have, okay, what do we have stacked up on the right-hand side? We have some amount of mercury, and then we have atmospheric pressure. So we'll write that. So PA prime equals some amount of mercury. How do we deal with the pressure? Just rho GH. Rho GH plus P atmosphere. Okay, what is atmospheric pressure in gauge pressure? We go back up to our picture. So if we're using gauge pressure, what is atmospheric pressure? But that's the definition, so 0. So working in gauge pressure in a lot of these situations, if you have atmospheric pressure hanging around, it's easier to work in gauge pressure. It makes your life easier because atmospheric pressures cancel out. So you can work in either pressure system and get the right answer, but oftentimes it's easier to work in gauge pressure. So we'll write this PA equals rho GH plus 0 kPa gauge. Just to remind ourselves that that's why we got rid of atmospheric pressure. Then our problem is super easy. So we just set PA equals PA prime. So we have 250 kPa equals rho GH. And then it just becomes a unit game. So rho of mercury, remember that the specific gravity is 13.5. So this is 13.5 times the density of water, right? So times 1,000 kilograms per meter cubed. And then G equals 9.81 meters per second squared. So we have 250 kilopascals, which is equal to 250,000 pascals, which is 250,000 so joules per meter cubed, or well, I'll just leave it at joules per meter cubed. So we have 250,000 joules per meter cubed. Right. One of the kind of interesting things about pressure, it's like a per volume energy. It's another way to think about it, right? That's how the units work out. Joules is energy. Pressure is an energy per volume, or it's a force per area. So those are kind of the two, I don't know, those are the two ways that I remember the units. It's an energy per volume, force per area. I don't know, kind of an interesting way to think about pressure. So this would be equal to, so now it's 13,500 kilograms per meter cubed times 9.81 meters per second squared times h. And we could figure that out. Just to figure out the units, we would end up with h in meters. To get all the units to work out. Right, and you could play with some of the units there to figure that out. We'd end up with h in meters, and h equals, well, let's make you go through the math, 1.132 meters. So there are lots of different types of manometers and shapes of manometers. As I said, they're used all the time because it's like a quick and easy way to do pressure change. I think it's also a nice, like we spend some time on it because it's a relatively easy way to be able to track, okay, how do pressure changes in fluids? It's also, right, it's a very common technique that you've all heard of. You've heard of barometric pressure. Barometric pressure is just like a specialized version of a manometer, right? So a barometer, we're not going to do anything else with this, but because we have 2 minutes, you would have something like this, where you have a really good vacuum, close to perfect, and then you have your fluid, and then you'd have like one side open to P atmosphere, and this height would be your barometric pressure. Right, which is like 30 inches of mercury, something like that. 29 point, it depends on the day, but about 30 inches of mercury. But you can, yeah, so it's a common technique used in that. It's common throughout industry because it's easy. The way that, especially when you get strange geometries, and you'll have some chance to work with through this in your homework, the math is not hard. It's just kind of figuring out, okay, what's the total weight on one side, what's the total weight on the other side, and kind of adding those up and setting those equivalent. So we'll get some chances to do that more in homework. When we come back on Wednesday, we're going to look at how do we do submerged surfaces and things that are not necessarily straight up and down. So we'll have a chance to do that. We should finish up fluid statics next time on Wednesday. But look for kind of more stuff about the upcoming exam and stuff kind of tomorrow or Wednesday and really beginning of next week. But hope you guys have a good Monday. We'll see you on Wednesday.